Good afternoon, all of you. This is lecture number 5 of your subject Microwave and Radar Engineering. In this video lecture, we are going to cover Introduction to Microwave Devices. Unit 2 consists of microwave devices. It is of two parts, microwave tubes, and second part is microwave semiconductor devices. In microwave tubes, we are going to cover Klystron, reflex Klystron, cross-field devices like Magnetron. Semiconductor devices, we are going to cover principle of Gunn, IMPATT, TRAPATT, bipolar transistors, MESFETs, etc. So first of all, we will able to find out what is the need of such microwave devices, special type of microwave devices at microwave frequencies. At microwave frequencies, the normal devices which we use generally like MOSFETs, diode, PN junction diode, BJT, and like FET or MOSFET that are confined to be used at lower frequencies below 300 megahertz, and above 300 megahertz such devices cannot be used, and a special type of microwave devices are necessary for such frequencies. So those devices which are not suitable for microwave frequencies are called as the conventional active devices, or conventional tubes, or conventional devices of conventional semiconductor devices. And the devices which are generally used at microwave frequencies, we generally call them as microwave devices, microwave tubes, microwave semiconductor devices. Okay, so basically these are the factors which are responsible why conventional devices fail at microwave frequencies, and why we need a special type of specially designed microwave devices at such frequencies. So these are the 6 factors which are going to discuss in this particular lecture in the coming slides one by one in detail. So first is the inter-electrode capacitance, second is lead inductance, third is transit time, fourth is gain bandwidth product, fifth is skin effect, and sixth one is dielectric loss. So let's go one by one and talk about the detail about each and every point and what actually they mean. So first of all, what is inter-electrode capacitance? See, in any kind of device, semiconductor device or any kind of device, you will see that there are, either in case of the PN diode, two electrode will be there. Like first is the anode and the other is the cathode. Like P is the anode, N region is the cathode. In case of the transistors, like in BJT, there are 3 electrodes, like base, collector, and emitter. So any kind of electrode you can see within the electrodes, there is one capacitance that is generated. It is not physically connected here, but as these electrodes are having a lot of the potential difference between them, so such capacitance come into effect. So such capacitance you can see here. These are the, for example, this is the gate, and this particular K is the cathode, and this is the anode, for example. So these 3 types of capacitances is shown here, like gate to cathode capacitance. Okay, so such capacitance are having uh, the capacitive reactance, which is inversely proportional to frequency with this formula. So at microwave frequencies, वो बंद कर देना. At microwave frequencies, what happened? The capacitive reactance becomes very low. At high frequency, the value of Xc is very low. So as Xc reduces, so at frequency you can say The microwave frequency can be considered the frequency which are approximately equal to infinity. So Fc become approximately equal to 0. So it means you can say that they usually short circuits the electrodes, or there is a short circuit that can exist between the inter-electrodes. Okay, because of the inter-electrode effects. So such short circuit will going to reduce the gain of the device, and definitely it reduce the performance of the device. You see, if a short circuit occur here between gate and cathode, so any current which is coming from here will not go to the actual circuit, and it gets grounded. Most of the current get directly grounded with a short circuit. And at the output also, the same thing happened. The current will not be delivered to the load, and the load voltage will assume to be zero. So definitely if the output voltage reduces or the input current or voltage reduces, the gain definitely reduces, because the gain is equals to output voltage upon input voltage or output current upon input current. Okay. So definitely if you want to minimize this effect, if you want to minimize the effect of reducing Xc with increasing Fc, so what you will do, you should increase this inter-electrode distance. Okay, so the distance, if you increase the distance, definitely the capacitance will going to increase, because capacitance of the device is equals to epsilon A upon D, where D is the distance between the plate of the capacitor, C is the capacitance, A is the area of the plates, and epsilon is the constant. So if you increase D, so if you increase D, C will reduce. If C will be reduced, Xc can be compensated. So means this means you have to make a, you should design a bigger device, that it should have a larger distance between the electrodes. But such conditions is not possible if you are working with the conventional devices, because if we talk about the chip, if you talk about small circuits like if we talk about the chip, there is a lot of millions of transistors in a single chip, and they perform a lot of function. So you can't use microwave frequency for such dedicated functions. But if you want to use the microwave frequency, you should realize some other application, and you should design some other type of circuit to make use of such frequency for such different application. So definitely microwave frequency cannot be used inside a hardware or a circuit which uses a highly compact chip with high density transistors of smaller sizes in nanometer. Now next is lead or stray inductance. See, as the capacitance we have seen, there is a inter-electrode capacitance between the plate of the electrodes, between the electrodes. That electrode act as a plate of the capacitor, and the distance between them, or the whatever the medium, it acts as a dielectric. Okay, whether it is air or vacuum. So here, similarly, the lead inductance come into effect. This inductance is not actually connected physically here, but because of the frequency, because of the resistance of the device, and the physical characteristics of the wiring, these are induced in the leads. Okay, so such inductance is called the lead inductance, and with the increasing frequency, their inductive reactance also increases, and at a very microwave frequency or high frequency, these inductive reactance is very high. So sometimes the conventional devices, if we talk about the conventional devices, the due to the lead inductance, the these electrode appear as an open circuit. to the input as well as open circuit to the ground. So whatever the current is coming from here or voltage coming from here will be dropped in the midway and will not reach the actual device. So this is also limits the gain of the circuit. And definitely if the ground connection also breaks, so this will also lead to the floating of the device in case of the MOSFET also. So definitely this is not good at high frequency, and this happens if you use the conventional device at microwave frequency. Okay, so the inductance of the cathode leads is common to both grid and plate circuits. This provides a path for degenerative feedback. Definitely, this become like a degenerative effect, like the effect which is not good, or which will not provide any amplification to the circuit, and will reduce the overall efficiency of the circuit. Okay. So transit time is the time taken by the electron to reach from cathode to the anode. Okay, let's suppose we are taking an example of the diode here. Here it is the N region of the cathode, and here it is the P region or the anode. And for example, a positive cycle is coming. If you supply AC signal here, in case of positive cycle, the P terminal will experience a positive supply and N will experience a negative supply. So the electrons are reflected from the N-type region and they are reflected to the P-type region as P is positive. So the time taken by the electron to move from N to P is the transit time, and it does not affect so much in case of the lower frequency. But as the frequency becomes higher, you can say the speed of the oscillation increases. The speed of the oscillation increases, and there is the changing cycle become very fast, like positive negative, so fast, like uh, they are so fast. They're in the speed is much faster, and it is much faster as compared to the transit time of the electron. So it will be a problem for a conventional device because there the transit time become very effective, or you can say become very considerable or significant as compared to the clock frequency or the signal frequency or the signal speed. See, if the frequency is high, so whenever there is a positive cycle, and negative cycle will come so fast because frequency and time are inversely proportional. So let's suppose if there is a gigahertz frequency, so the changing cycle will be within, you can say, nanoseconds, and if you say the transit time is in microseconds, so there is a problem. If the electron will go from here to here, and in a midway the cycle changes, so it should go back to its original position. So it will not travel this path. So this will result in the decrease in the efficiency of the device because the electron will not able to complete its oscillatory cycle, and this will result means higher transit time as compared to the uh, changing time or speed of the frequency or at higher frequency. So this become very appreciable at that time, and such things should be avoided. So in case we should need certain devices where you can compensate for the transit time. Okay, so certain types of devices we require at microwave frequencies. Gain bandwidth product. In case of any kind of device, amplifier or any kind of, you can say, transistors, the gain bandwidth product is always constant. Means if the gain is, you can say, infinity, the bandwidth is zero. Okay. Or if the bandwidth is high, the gain is low. If the bandwidth is low, the gain become very high. So there is a, if you want at microwave frequency, your device will offer higher gain. So you should use narrow frequencies to compensate for higher gain. So you know that we are using microwave frequency because we are having an advantage of a larger bandwidth. Why should we compensate for the bandwidth to get the higher gain? So for certain devices, conventional devices, The bandwidth offered at microwave frequency is very low, or you can have narrow bandwidth is there. That's why we don't use microwave frequency with conventional devices. Also, the quality factor is inversely proportional to frequency to bandwidth. At a large bandwidth, the Q value become very low. So the selectivity of a particular frequency also become lower. And definitely, even if the gain bandwidth product is independent of frequency, but it depends on bandwidth. And larger bandwidth means a smaller gain. Or you can say if you want a larger gain, so you need to shrink the bandwidth. So this is not, you can say, a good idea. So even instead you can use better devices like microwave devices at such frequencies. So in this you can see is about the skin depth. Skin depth is the distribution of the current from the skin towards the center of the wire. This is the cross-sectional area of the wire when you cut the wire, and if you see the cutted portion with your eyes, you see the wire will look like a circle. And as the frequency increases, the current at the center will become zero nearly, and the at a much higher frequency the current is only confined to the smaller cross-sectional area, or a smaller surface of the device. Okay, so you can see here, this is the skin. Here the skin depth is infinity. Here the skin depth slightly reduces, and here the skin depth is becoming very less. Only the surface of the wire is containing the current, and a large portion of the wire is not containing any current across the cross section. At microwave frequency, the frequency become very high. So the skin depth become very less. Or infinity frequency, skin depth is zero. At DC, skin depth is infinity. So at, you can say that at microwave frequency, if you use conventional devices, all of the current will not be delivered, and definitely there are losses due to skin effect, because the skin effect come into account at microwave frequency because the skin depth reduces. Okay, next, dielectric losses. See, in all kind of you can say MOSFET. Here this is silicon dioxide which is present above the channel. This is the channel. This is the enhancement type N MOSFET, and these are the N diffusion region. One is the source, one is the drain, and this is the substrate. So any kind of, you can say, if you, whenever the gate is given a high voltage, the channel is formed between source and drain, and if the source is grounded and drain is positive, electron will flow from source to drain. Source supply the electron, drain collect the electron. So whatever it may be, if it is P type of MOSFET, it does the same thing. Source is the provider of the majority carrier and drain is the collector of the majority carrier. The same thing happens in the transistors also, like emitter, base and collector was there. And base is a control electrode, whereas this emitter is the supplier of the majority carriers, and the collector is the collector of the majority carriers. So definitely, whenever if we talk about the N-type devices, the electron will flow from source to drain, and the current will flow from drain to source. Always the current will flow from drain to source, whether we talk about the um, N type of devices, because the flow of the majority carriers are from source to drain. Now here, although the source is grounded and drain is at high voltage, and this is the oxide layer which is between this gate and the channel. The use of the oxide layer is done in any kind of MOSFET in order to uh, provide the insulation between the channel and the gate. Because the channel which is containing the electrons, minority current electron from the P substrate, should not cross the this should not reach the gate electron, because gate electrode only acting as a control electrode. So we have to just provide the voltage here so that a channel is physically formed, Whenever the channel is not formed or the gate voltage is not supplied, the MOSFET is off, and whenever the supply is there, the MOSFET considered to be on. So definitely oxide layer is having its importance, and we're not talking about how MOSFET works in this particular lecture, but you know now oxide layer is there. But at microwave frequency, what happened? Dielectric losses increases, and at microwave frequency above 300 megahertz or especially above 1 gigahertz, oxide layer cracks or breaks at microwave frequencies. If the layer will break, so it will result in the short circuit between the substrate and the gate. And if the short circuit will occur, the device will run. Okay. Also, the oxide layer is important in order to isolate between the adjacent devices. As you know that in a chip or any kind of IC, the transistors are very closely packed because of the we want a highly sophisticated functions out of a single chip, and there are a lot of millions of transistors in a chip, so they are very small size, they're very densely packed, the chip is very compact, so oxide is definitely required in order to provide insulation. And here you can see a coaxial cable also, you can see this is the dielectric which is present between the outer insulation or a shield and an inner conductor. This is the conductor which carries the signal. You can see such type of coaxial cable previously in our TV to connect the antenna to the TV. But nowadays also the set-top in the set-top boxes, the dish and antenna is connected to the set-top box with a coaxial cable only. So this is the inner conductor which carry the signal. So this conductor definitely, definitely we use down conversion, so that down conversion is converting the gigahertz frequency down to megahertz so that it can be processed easily. Otherwise, this dielectric will get break, and the signal which is confined here will radiate to the surrounding, and there will be signal losses. So any kind of dielectric, if it breaks, it definitely leads to dielectric losses, and it definitely results in the radiation of the signal from the device, and this results in losses and reduction in the gain and reduction in the efficiency of the devices. So it is not good. So what happens? What we generally do, we design a special type of devices at microwave frequency, especially we talk about the devices. So, and if we directly want to process such microwave frequencies through certain devices, we need a different types of devices that are free from dielectric losses. Okay. I mean, dielectric should not be there. Now, conclusively, what we have studied here that at microwave frequency of from 300 megahertz to 300 gigahertz, conventional devices will underperform and leads to losses and signal attenuation. And second thing what we have learned is at higher frequency, a special type of microwave generator amplifiers are required. And third, microwave devices are designed to perform well at microwave frequency without considerable losses and signal attenuation. So this is the 3 points in which I have concluded my lecture, and I hope you will get it. And thank you all of you. So I hope you are visiting frequently in Moodle CMS for notes and updated lecture links. Also, if you are having any doubt, please mail me. This is my mail ID. And please also revise your lectures by frequently visiting the YouTube channel also. And I hope you are doing well, and please be prepared for all the tests which I will going to update in Moodle CMS. And you can also view certain videos related to how to attempt the test in Moodle in my YouTube channel. And all the best. And I just want to say that this is a very simple, or you can say that the subject is very good until unless you develop your interest. Okay, all the best. Thank you.